You're responsible for that big, essential machine. Could be pumps, fans, conveyors, whatever. Stuff that absolutely cannot stop without costing a fortune.
Right, the mission-critical gear. And often it's powered by medium-voltage drive systems.
Exactly. VFDs, transformers, motors. It can feel, well, pretty complex to navigate, especially when the stakes are so high.
Uh-huh. Downtime isn't just an inconvenience, it's serious money lost.
So today, we're diving into the sources you've sent us. This is really for you listening if you're an electrical engineer, a project manager, maybe in purchasing, or an operations manager. We want to help you cut through all that noise.
And find those key insights, right? The things that really matter for keeping these systems reliable, efficient, and safe. The pain of failure is just huge.
It really is. Lost production, big repair bills, it all adds up. So understanding the choices you make about these MV drives is, well, it's vital.
Okay.
And looking at the sources, something jumps out immediately. The transformer. It's apparently much more than just a voltage changer in MV drives. My source says you almost never see a source inverter drive without one.
That's a great point the sources make. The transformer provides essential electrical isolation. Think of it like a buffer, a first line of defense.
A defense against what exactly?
Against grid disturbances, mainly. Voltage spikes, transients from the utility, switching things around. It protects the drive's sensitive electronics.
So it's like a shield, keeping the grid chaos out.
Pretty much.
Yeah.
It also limits the potential short-circuit current if there's a fault inside the drive, making things less, well, catastrophic.
Okay, that makes sense.
And critically, it lets you operate ungrounded on the drive side. So a single ground fault might not immediately trip your whole system offline. That's a massive plus for availability.
Right, keeping things running.
Plus, those special multi-phase transformers, the ones with precise phase shifts, they naturally cancel out a lot of the problematic line harmonics. Helps keep the power grid clean.
Harmonics. That's the messy power signature drives can create because they chop up the AC, right, instead of a smooth sine wave.
Exactly. They're nonlinear loads. And those harmonics can cause trouble for other equipment connected nearby. Your sources correctly mention converter duty transformers are built tougher for this.
Built to handle the extra heat and the specific demands.
Yes, and those phase shifts are key for handling harmonics, as we said. This brings up another big topic from your sources, the drive's design, its topology.
Okay, topology. How does that internal design affect things? The sources talk about levels and pulses. Let's start with levels. What does that mean for the motor?
Levels refer to the quality of the output waveform going to the motor. A simple basic drive, say a 2-level one, gives the motor a pretty rough, choppy voltage, lots of square edges.
Right, not very smooth.
But as you increase the levels, 3-level, 5-level, or even multi-level designs like the cell-based ones, M2C, for example, you get many more, much smaller steps.
So it starts looking much more like a smooth sine wave.
Precisely. And that's incredibly motor-friendly. It cuts down harmonic heating in the motor, reduces stress on the insulation, a big failure point, and minimizes torque pulsations. Smoother running, longer life.
That sounds like a big win. Your sources also mention some topologies are good for retrofits. Less need for extra filters.
That's right. Some multi-level types produce such a clean output they often don't need bulky, expensive output filters, even on older motors. Huge benefit for project managers and purchasing folks thinking about upgrades.
Got it. So levels impact the motor side. What about pulses? That's tied to the input, the grid side.
Correct. Pulses relate to how the drive draws current from the grid. A basic rectifier creates significant input harmonics.
The same problem, but on the input side.
Yes. But using those special converter transformers we talked about with multiple phase-shifted windings allows for higher pulse counts, 12 pulse, 18, even 24 pulse.
And more pulses means cleaner power draw.
Fundamentally, yes. Higher pulse numbers inherently cancel more of the lower-order harmonics. Cleaner grid interaction. Alternatively, an active front-end, or AFE, topology can also achieve very low harmonics.
Okay, so the topology choice hits both the motor's health and grid compliance. This all ties directly into reliability, doesn't it? Mean time between failure, mean time to repair MTBF and MTTR.
Exactly. MTBF, how long it should run before a failure. For critical gear, you want that number sky high, think over 100,000 hours, 10+ years.
And MTTR, that's how fast you fix it when it does fail.
Yes. And minimizing that is crucial. As any operations manager knows, downtime is just, well, it's bleeding cash. Every minute counts.
What helps drive down that repair time, the MTTR?
Things highlighted in your sources include modularity. How easy is it to swap a failed part, like a power cell? Fault containment within the drive helps too, and vendor support is massive skilled techs, parts availability, remote diagnostics.
Remote support can save a site visit sometimes.
Absolutely. It can slash troubleshooting time. Now, for building that high MTBF, high reliability from the start,
What's key there?
redundancy is a big one. A full duplicate drive is often too expensive for MV, but cell-based topologies often allow for N+1 redundancy.
Meaning you add just one extra power cell.
Right. One extra cell beyond the minimum needed. N. If any single cell fails, the spare takes over instantly. You replace the bad one later during planned maintenance. Big boost to MTBF.
So it's not just about good components, but smart design like redundancy.
And overall system engineering, how everything integrates. The network, the motor, the environment, it all plays a part.
Which brings us back to the decision-making. Your sources really push looking beyond the initial price tag, right? Thinking about the total lifecycle cost, or LCC.
This is so critical, especially for assets running for decades. The initial CapEx is often dwarfed by the OpEx energy, maintenance, spares, service over 20 or 30 years.
So a cheaper drive might cost way more in the long run.
Often, yes. Investing a bit more upfront and higher reliability, better efficiency, maybe better support, can drastically lower that total LCC. And most importantly, it minimizes that brutal cost of unexpected downtime.
You really need to know what an hour of downtime actually costs your specific operation.
Exactly. That data helps justify the LCC approach.
Okay, so wrapping this up, this dive really shows that for critical machines, getting MV drive systems right means understanding things like the transformer's protective role.
And how the drive's topology, the levels and pulses, impacts the motor and the grid.
Right. And reliability isn't just one thing. It's robust design, maybe N+1 redundancy, good system engineering, affecting MTBF and MTTR.
And ultimately, looking past that initial cost to the total life cycle cost is key to minimizing downtime over the long haul.
It definitely seems the smartest approach.
So the real question becomes, in this complex landscape with so many options and claims, how do you ensure you're asking the right questions for your specific needs?
And how do you effectively evaluate the answers you get? Something important to think about.
Definitely.
For practical solutions and expert advice tailored specifically to your power drive system requirements, why not reach out? Let's make sure your critical machines are driven reliably, efficiently, and safely.